Imagine standing on a world where the sky rains glass sideways at 5,400 miles per hour. Or picture yourself on a moon where geysers shoot ice 500 miles into space, feeding a planetary ring system with fresh water. A place where an entire ocean containing more water than all of Earth's seas combined hides, beneath a shell of ice just waiting to tell us if we're real alone in the universe. What about a world so volcanically active that its entire surface gets resurfaced every million years? Where sulfur lava flows glow in the darkness, and the ground literally explodes beneath your feet every few hours. Here's what most people don't realize. Earth is the boring one. We live on the most geologically stable, atmospherically calm, temperature-moderate rock in the entire solar system. We read the vanilla ice cream of planets in a cosmic ice cream shop that serves flavors like metallic hydrogen nightmare and sulfuric acid death storm. For the past 70 years, we've been sending robots brave, expendable robots to explore our cosmic neighborhood. And what they've found would make science fiction authors throw up their hands and say, that's too unrealistic. We're talking about worlds where it rains diamonds, moons have moons, and we didn't know that was possible. Lakes exist made of liquid methane at negative 290 degrees Fahrenheit. Mountains tower 3 times higher than ever. Storms rage for centuries, large enough to swallow 3 Earths. This isn't speculation. This isn't theory. This is what's actually out there, confirmed by Voyager, Cassini, Galileo, New Horizons, and dozens of other missions that have fundamentally rewritten our understanding of what a planet or moon even means. So buckle up. For the next 2 hours, we're taking a journey to the most unusual, most extreme, most absolutely bizarre worlds in our solar system. We're going to visit places where physics operates at the edge of what's possible, where chemistry creates landscapes that shouldn't exist, and where the question, could life survive here, has some genuinely disturbing answers. Welcome to the freak show of the solar system. And trust me, Earth's invitation got lost in the mail because we're way too normal for this club. Let's start our journey with a world that makes Dante's Inferno look like a pleasant vacation spot. Our first stop is 390 million miles from Earth, orbiting the largest planet in the solar system. And if you're thinking, oh, we're going to Jupiter, that'll be cool, I have news for you. We're not going to Jupiter. We're going somewhere worse. Meet Io, Jupiter's innermost large moon. And here's the thing about Io, it's the most volcanically active body in the entire solar system. Not more active than Earth. Not pretty active for its size. I mean, it has over 400 active volcanoes erupting right now as you watch this. To put that in perspective, Earth has about 1,500 potentially active volcanoes total, and only about 50 erupt in any given year. Io has 400 erupting simultaneously, always, without pause, for billions of years. The surface of Io looks like someone took a pizza, deep-fried it, then bombed it with sulfur and lava. It's covered in yellows, oranges, reds, and blacks, all from sulfur and sulfur dioxide in various states. There's almost no impact craters because the surface gets completely resurfaced every million years or so. Any craters that form just get buried under fresh lava. Now you might be wondering, why is this small moon roughly the size of Earth's moon so absurdly volcanic? The answer is one of the most brutal demonstrations of physics in the solar system: tidal forces. See, Io orbits Jupiter at only 262,000 miles closer than our moon orbits Earth, and Jupiter is massive. We're talking 318 times Earth's mass. The gravitational force Jupiter exerts on Io is tremendous, but here's where it gets nasty. Io is also locked in an orbital resonance with Jupiter's other large moons, Europa and Ganymede. For every orbit Io makes around Jupiter, Europa makes 2 and Ganymede makes 4. This creates a gravitational tug-of-war. The result? Io gets squeezed and stretched like a stress ball. Its solid surface rises and falls by up to 300 feet Imagine the entire ground beneath your feet, rising and falling the height of a football field every 42 hours. This constant flexing generates tremendous heat through friction. We're talking about Io's interior being heated by 200 trillion watts of power. That's 200 times the total energy output of all human civilization. And all that heat has to go somewhere. So it explodes outward in the form of the most spectacular volcanic eruptions you can imagine. Some of Io's volcanic plumes shoot material 300 miles into space. That's high enough to reach the International Space Station if Io were Earth. The largest volcano, Loki Patera, has a lava lake covering 127 miles in diameter, larger than the entire state of Connecticut. And it's not normal lava. This stuff reaches temperatures up to 3,000 degrees Fahrenheit, which is hot enough that the lava glows white hot, not red. Then there's Prometheus, a volcano that's been continuously erupting since at least 1979, when Voyager 1 first spotted it. That's 45 years of non-stop eruption, and it's probably been going for millions of years before we showed up to watch. The plume from Prometheus shoots 75 miles high and creates a deposit ring 180 miles across. Imagine a single volcano on Earth that covered everything from New York to Boston in volcanic debris. That's one volcano on Io, and it's not even in the top 5 for intensity. The most powerful eruption ever observed was from Peel in 1979. The plume reached 300 miles high and deposited a red ring of sulfur compounds over an area larger than Alaska. This single eruption ejected more material than Mount St. Helens, Krakatoa, and Vesuvius combined. And it was just a Tuesday on Io now. Io does technically have an atmosphere. I use that term loosely. It's mostly sulfur dioxide gas from all the volcanic eruptions, and it's so thin that the atmospheric pressure is 1/billionth of Earth's. You couldn't breathe it, not just because it's toxic, but because there's essentially nothing there to breathe. The atmosphere is constantly being stripped away by Jupiter's intense magnetosphere. But Io just keeps pumping out more gas from its volcanoes, maintaining this incredibly tenuous toxic envelope. And here's where it gets weird. Io has auroras. Not like Earth's pretty green curtains Io. These auroras are created by volcanic gases being ionized by Jupiter's magnetic field. They glow in ultraviolet light, invisible to human eyes, but captured by spacecraft instruments. So you'd be standing on a moon where the ground is constantly exploding, the sky is glowing with invisible light, and you're being bombarded by Jupiter's radiation belt, delivering 3,600 rem per day. For context, 400 rem is lethal to humans. You'd be getting 9 times the lethal dose every single day. The total heat output from Io is about 100 trillion watts, enough to power human civilization 100 times over. And here's the kicker. Despite all this volcanic activity, Io is losing heat faster than it's generating it. Wait, what? Io radiates heat into space so efficiently that it's actually cooling down over geological time. The tidal heating from Jupiter is immense, but the moon is so active that it's essentially bleeding heat into the vacuum of space through its constant eruptions. This means Io is in a race against time. Eventually, we're talking billions of years, the interior will cool enough that the volcanic activity will decrease. But for now, it's trapped in this hellish cycle of being squeezed, heated, and exploding. Oh, and did I mention Io has mountains? Not shield volcanoes like Hawaii actual mountains, formed by compression and uplift. Some reach 16 kilometers high, nearly twice the height of Mount Everest. How do you get mountains on a world that's constantly resurfacing itself with lava? Scientists think they're formed by the crust being compressed by all that tidal stress. The ground gets squeezed so hard that it buckles upward, forming massive peaks. Then lava flows around them, and the whole bizarre cycle continues. The surface of Io is a palette of chemical madness. Yellow sulfur, white sulfur dioxide frost, red and orange sulfur compounds, black silicate lava flows. It looks like an abstract painting created by a chemist having a breakdown. There are regions called Pateray shallow volcanic craters that look like someone scooped out chunks of the surface with an ice cream scoop the size of a city. These can be 25 miles across and are filled with cooling lava lakes. But Io's influence extends far beyond its surface. The volcanic eruptions eject material that gets caught in Jupiter's magnetosphere, creating what's called the Io plasma torus, a donut-shaped cloud of ionized particles surrounding Jupiter at Io's orbital distance. This torus contains sulfur and oxygen ions and glows faintly in visible light. It's essentially Io vomiting material into space, and that material then gets trapped in Jupiter's magnetic field, creating this massive structure that's 3,000 times bigger than Io itself. The electrical current flowing between Io and Jupiter is about 3 million amperes, roughly equivalent to the combined electrical usage of 10 major cities. This current creates an auroral footprint in Jupiter's atmosphere, directly connected to Io's position. So Io is literally electrically wired to Jupiter, transferring millions of amps of current through a magnetic field line. It's the most powerful naturally occurring electrical circuit in the solar system. Let's imagine, for a moment of masochistic curiosity, what it would be like to land on Io. First, you'd need a spacecraft capable of withstanding radiation levels that would fry electronics in minutes. Then you'd need to find a landing spot that isn't actively erupting. Good luck with that, given the 400 active volcanoes. Assuming you found a safe spot, you'd step out onto a landscape of sulfur compounds in various states. The ground would be unstable fresh lava flows, cool and crack constantly. You'd need to move quickly because volcanic eruptions are frequent and unpredictable. The sky would be a murky yellow-brown from volcanic gases. Jupiter would dominate the sky, appearing 11 times larger than our moon looks from Earth. The gas giant would be a swirling mass of clouds, and you'd be able to see the shadow of Io racing across Jupiter's face during transits. Every 42 hours, you'd feel the ground literally rising and falling beneath your feet, not from an earthquake, but from the solid body tide caused by Jupiter's gravity. 300 feet of vertical movement. Buildings would need to be designed to handle that kind of flex, which is insane to think about. Then, without warning, a volcanic plume would erupt a few dozen miles away. You'd see the column of gas and debris shoot into the sky, reaching the edge of space. The material would arc over and begin raining down not water, but sulfur dioxide, snow, and sulfur compounds. The ground would shake from the eruption. Then another volcano would go off, and another. Because on Io, it's always volcano o'clock. Io is a reminder that the universe doesn't care about our comfort zones. It's a world where the laws of physics are pushed to extremes, where stable and safe are concepts that simply don't apply. It's a moon that has been described as the pizza from hell and the most hostile surface in the solar system, and both descriptions are accurate. But here's the thing, Io isn't even the weirdest moon in the Jupiter system. Because just 148,000 miles away from this volcanic hellscape is a moon that might harbor life. A moon covered in ice that hides an ocean, containing twice as much water as all of Earth's oceans combined. But before we visit that frozen water world, we need to talk about a planet that makes Io's surface look inviting by comparison. Let me tell you about the closest thing to hell we've found in the solar system. And no, it's not a moon. It's our sister planet. From space, Venus looks gorgeous. A brilliant white sphere, the brightest natural object in our night sky after the moon. Ancient, astronomers named it after the goddess of love and beauty. Then we sent probes there. And we realized we'd named it after the wrong deity. This isn't Venus. This is hell with a PR team. Venus is Earth's twin, similar in size, mass, and composition. It's 95% of Earth's diameter and 82% of Earth's mass. It orbits at 67 million miles from the Sun, compared to our 93 million. It should be a slightly warmer version of Earth. Instead, it's an apocalypse. The surface temperature on Venus is 864 degrees Fahrenheit. That's hot enough to melt lead. Hot enough that your spacecraft's metal components would literally liquefy. It's hotter than Mercury, despite being twice as far from the Sun. How is that possible? The answer is the most extreme greenhouse effect in the solar system. Venus's atmosphere is 96% carbon dioxide, the ultimate thermal blanket. This CO2 traps heat so efficiently that the planet's surface temperature hasn't varied significantly in billions of years. But the heat is just the opening act. The atmospheric pressure at Venus's surface is 92 bars. That's 92 times Earth's sea level pressure. It's equivalent to being 3,000 feet underwater on Earth. If you stood on Venus ignoring the heat, that would vaporize you instantly. The atmospheric pressure would crush you like a soda can. Your lungs would collapse, your bones would crack, and the dense atmosphere would compress your body into something resembling a pancake. The Soviet Union tried landing probes on Venus multiple times. Most were destroyed during descent. The ones that survived landing lasted minutes before being cooked and crushed. Venera 13, the most successful lander, survived for 127 minutes in 1982. It sent back the first color images of Venus's surface before the electronics fried. The images show a hellish landscape of flat rocks under an orange sky. Those rocks? They're basalt, volcanic rock, similar to what we find on Earth. But on Venus, they're at oven temperatures. If you touched one, your hand would char instantly. The sky in those images has an orange glow, not because of the rocks, but because of the atmosphere. The thick CO2 atmosphere scatters light in strange ways, creating this perpetual orange twilight at the surface. And the atmosphere is so dense that light bends noticeably. If you stood on Venus and looked at the horizon, you'd see a curved, distorted view because of atmospheric refraction. The world would look warped. But wait, it gets worse. The clouds on Venus, those beautiful white clouds we see from space, are made of sulfuric acid, concentrated sulfuric acid, the same stuff you'd find in a car battery, but in droplet form, suspended in clouds 30 miles above the surface. These sulfuric acid clouds reflect most of the sun's light, which is why Venus looks so bright from Earth. But it also means the planet has acid rain. Except the rain never reaches the surface because it evaporates in the extreme heat of the lower atmosphere. And then there's the rotation. Venus rotates backwards compared to most planets. While Earth and the other planets spin counterclockwise when viewed from above the North Pole, Venus spins clockwise. This is called retrograde rotation, and scientists still aren't entirely sure why. One theory: Venus was struck by a massive object early in its history that knocked it into a backward spin. Another theory: atmospheric tides from the sun gradually slowed Venus's rotation until it reversed. But here is the truly bizarre part. Venus rotates so slowly that a single day on Venus 1 complete rotation takes 243 Earth days. Meanwhile, Venus orbits the sun in 225 Earth days. Read that again. A day on Venus is longer than a year on Venus. If you stood on Venus's surface, ignoring again the fact that you'd be simultaneously melted, crushed, and suffocated, you'd experience one sunrise and one sunset per year. And because Venus rotates backwards, the sun would rise in the west and set in the east. Except you wouldn't see the sun at all, because the thick clouds never clear. And then there's the wind. At the surface, winds are gentle, maybe 3 to 6 miles per hour. But high in the atmosphere, where those sulfuric acid clouds float, the winds reach 224 miles per hour. That's twice as fast as any hurricane on Earth. These winds circle the entire planet in just 4 Earth days, a phenomenon called superrotation. The atmosphere is moving 60 times faster than the planet itself rotates. How? Scientists are still trying to figure it out. It shouldn't be possible based on our understanding of atmospheric dynamics, but Venus doesn't care about our understanding. Oh, and there's lightning. Constant lightning. Venus has more lightning activity than Earth, with massive electrical storms raging through those sulfuric acid clouds. Imagine, you're in clouds made of battery acid, winds screaming at over 200 miles per hour, and lightning bolts arcing every few seconds. That's the middle atmosphere of Venus. The surface of Venus is dominated by volcanic features. About 85% of the surface is covered by volcanic plains, and there are over 1,600 major volcanoes and volcanic features identified. Some of these volcanoes are massive. Mount Mons rises 5 miles above the surrounding plains. Sapus Mons is surrounded by enormous lava flows that extend for hundreds of miles. But here's the question. Are these volcanoes still active? Recent data from Venus Express and ground-based observations suggest yes. Scientists have detected variations in sulfur dioxide levels in the atmosphere, which could indicate ongoing volcanic eruptions. They've also found regions where the surface appears to have fresh lava flows. In 2020, researchers discovered phosphine gas in Venus's atmosphere, a gas that, on Earth, is primarily produced by biological processes or extreme geological activity. The discovery sparked controversy because phosphine could potentially be a biosignature. But on Venus, it's more likely evidence of active volcanism or unusual atmospheric chemistry. Still, it reminded us how little we understand about this planet. Venus has no magnetic field. None. Earth's magnetic field protects us from solar wind and radiation. Venus? Naked to the cosmos. Why no magnetic field? Probably because Venus rotates so slowly that it can't generate the dynamo effect in its core that creates magnetic fields. Or its core might be completely solidified. Without a magnetic field, the solar wind directly impacts Venus's upper atmosphere, stripping away atoms and ions constantly. Venus is literally being sandblasted by the sun. Here's the tragic part. Venus wasn't always like this. Scientists believe Venus once had liquid water oceans. Billions of years ago, when the sun was dimmer and Venus's atmosphere was less dense, the planet might have been habitable. But something went wrong. A runaway greenhouse effect kicked in. The oceans evaporated. Water vapor, a greenhouse gas, trapped more heat, which evaporated more oceans, which trapped more heat, a vicious cycle. The water vapor was broken down by ultraviolet light into hydrogen and oxygen. The hydrogen escaped into space. The oxygen reacted with surface minerals. And Venus was left a desiccated hellscape. This is why Venus terrifies climate scientists. It's a cautionary tale of what happens when greenhouse effects spiral out of control. Venus shows us that Earth-sized planets in the habitable zone aren't automatically habitable. They can tip into permanent hell if the conditions are wrong. Earth and Venus started similarly. Earth got lucky, the right distance from the sun, the right amount of water, plate tectonics to regulate atmospheric CO2. Venus got unlucky, and it's been paying for it for billions of years. There are regions on Venus called tesserae, areas of highly deformed terrain that look like crumpled paper when viewed from radar. These are ancient crustal formations, possibly the oldest surfaces on Venus. Alpha Regio and Ishtar Terra are examples plateau-like regions that rise miles above the surrounding plains. Ishtar Terra is roughly the size of Australia and contains Maxwell Montes, the highest mountain on Venus at 7 miles tall. These tesserae might be remnants of ancient continents from when Venus had plate tectonics. Scientists think Venus' entire crust might have been resurfaced by massive volcanic activity about 300 to 500 million years ago, wiping out most ancient features. Then there are the arachnoids and coronae, bizarre circular features unique to Venus. Arachnoids look like spider webs formed by volcanic activity, with radial fractures extending from central points. Coronae are massive circular structures formed by mantle plumes, hot blobs of rock rising from deep within Venus. Some coronae are hundreds of miles across, like giant blisters on the planet's surface, where hot material tried to punch through the crust. These features don't exist on Earth because our plate tectonics prevents such localized mantle upwellings. Venus, without plate tectonics, gets these weird frozen scars from its internal heat trying to escape. Venus's atmosphere is stratified into distinct layers, each more hostile than the last as you descend. The upper atmosphere, at 40 to 60 miles altitude, is actually almost Earth-like. The temperature is around 85 degrees Fahrenheit, and the pressure is similar to Earth's surface. Some scientists have proposed floating cities in this layer balloons, filled with breathable air that would naturally float at this altitude, because oxygen and nitrogen are buoyant in a CO2 atmosphere, but below that, it's a descent into madness. At 30 miles altitude, those sulfuric acid clouds form. Temperature, 160 degrees Fahrenheit. Pressure, still tolerable. At 15 miles, 300 degrees Fahrenheit. Pressure climbing. At 6 miles, 570 degrees Fahrenheit. Pressure now 25 times Earth's sea level. At the surface, 864 degrees Fahrenheit and 92 atmospheres of crushing pressure. It's a temperature and pressure gradient that would destroy any human-made craft in minutes. Studying Venus is incredibly difficult. Most missions have been orbiters that study the planet from a safe distance. The Soviet Venera program was the only series of successful landers, and even they lasted less than 2 hours. NASA's Magellan mission, 1990 to 1994, mapped Venus's surface using radar, revealing the volcanic plains, tesserae, and bizarre features we've been discussing. But it did so from orbit, never attempting to land. There are plans for new Venus missions. NASA's Veritas will create high-resolution topographic maps. ESI's Envision will study the atmosphere and surface. India's Shukrayan-1 will focus on atmospheric composition. But landing on Venus and surviving long enough to do serious science? That requires technology we're still developing. Concepts include high-temperature electronics, advanced cooling systems, and rovers that can operate in extreme conditions. Some scientists propose clockwork rovers, mechanical devices with no electronics that could operate using the temperature differential between the surface and atmosphere. Others suggest balloons that float in the habitable layer and occasionally dip down to sample the surface. Venus is our closest planetary neighbor. It's a twin gone wrong, a paradise lost, a greenhouse cautionary tale. It's what happens when a planet's climate system breaks down completely and irreversibly. And it's a reminder that in the cosmic lottery of planet formation, Earth won the jackpot. We got the Goldilocks conditions, not too hot, not too cold, just right. Venus rolled the dice and got snake eyes. So that's Venus, a planet where the surface temperature can melt metal, the atmospheric pressure can crush. Submarines, the clouds are made of acid. It rains, but the rain never reaches the ground. A day is longer than a year. The sun rises in the west, and the wind screams at 200 miles per hour through an atmosphere 90 times thicker than Earth's. And somehow, Io's volcanic hellscape seems almost pleasant by comparison. At least on Io, you wouldn't be crushed, melted, and dissolved simultaneously. But now let's leave these hostile worlds behind and visit somewhere cold. Really, really cold. Let's talk about the ice moons. Because hidden beneath frozen surfaces in the outer solar system are oceans that might harbor life. And one of them has been shooting water into space for us to sample. If aliens exist in our solar system, Europa might be where we find them. This moon of Jupiter, about the size of Earth's moon, is one of the smoothest objects in the solar system. Its surface is water ice clean, white, and crisscrossed with reddish-brown cracks that look like blood vessels on an eyeball. But the ice is just the shell. Beneath that frozen crust estimated to be 10 to 15 miles thick, there's an ocean. a global ocean of liquid water that's 40 to 100 miles deep. Do the math. Europa's subsurface ocean contains roughly twice as much water as all of Earth's oceans combined. It's the largest ocean in the solar system, and it's been liquid for possibly billions of years. How does water stay liquid so far from the sun, where temperatures plunge to minus 370 degrees Fahrenheit? Same answer as Io, tidal heating. Europa orbits Jupiter every 3.5 Earth days, locked in that same gravitational resonance with Io and Ganymede. Jupiter's massive gravity flexes Europa's interior, generating heat through friction. But unlike Io, which is close enough to Jupiter to get absolutely brutalized by tidal forces, Europa's tidal heating is gentler, just enough to keep that subsurface ocean liquid without turning the moon into a volcanic nightmare. The surface of Europa tells the story of this ocean. Those reddish-brown cracks? They're called linea, and they're places where the ice shell has fractured and separated, allowing warmer ice or even liquid water to well up from below and freeze. The reddish color is probably from salts and organic molecules brought up from the ocean, and then irradiated by Jupiter's intense radiation, which chemically alters them. Some of these linea are thousands of miles long and can be dozens of miles wide. They crisscross the surface in a chaotic pattern, and they're constantly forming and reforming as the ice shell responds to tidal stress. Then there are the chaos terrain regions areas, where the surface has been completely disrupted into jumbled blocks of ice. These look like someone took a frozen lake, broke it into pieces, shuffled the pieces around, then let it refreeze in a scrambled mess. Scientists think chaos terrain forms when pockets of warmer ice or liquid water rise up from below, melting and disrupting the surface ice. It's evidence that Europa's shell is active, dynamic, and relatively young. And speaking of young, Europa has very few impact craters. Compared to the heavily cratered surfaces of older bodies like our Moon or Mercury, Europa is practically pristine. This means the surface is constantly being resurfaced, probably within the last 40 to 90 million years. For a moon that's 4.5 billion years old, having a surface less than 100 million years old is remarkable. It's like having a 45-year-old person with the skin of a newborn. But Europa's location comes with a severe penalty: radiation. Europa orbits deep within Jupiter's magnetosphere, one of the most intense radiation environments in the solar system. The surface receives about 540 rem per day, enough to kill a human in hours. This radiation bombards the ice, breaking apart water molecules and creating an extremely thin oxygen atmosphere. But it's not breathable oxygen. It's so tenuous that it barely qualifies as an atmosphere at all. The radiation also creates a major challenge for any mission trying to land on Europa. Spacecraft electronics would need heavy shielding, and surface missions would have limited operational lifetimes. But here's where Europa gets really exciting. In 2012, using the Hubble Space Telescope, scientists detected something incredible: water vapor plumes erupting from Europa's surface, reaching heights of 125 miles. Let me be clear about what this means. Europa is spouting water into space. Water from its subsurface ocean. Water we can sample without drilling through miles of ice. The plumes seem to occur in the same regions repeatedly, particularly around Europa's south polar region. They might be geysers erupting through cracks in the ice, driven by tidal pressure on the ocean below. If we send a spacecraft through these plumes with the right instruments, we could analyze the chemistry of Europa's ocean without ever landing. We could look for organic molecules, salts, even potential biosignatures. This is why NASA's Europa Clipper mission, launching in 2024, is so important. It'll make multiple close flybys of Europa, flying through these plumes and analyzing what they contain. But what's in that ocean? Scientists believe Europa's ocean floor is probably rocky, the same kind of rock that makes up the deep ocean floors on Earth. And if that's the case, there might be hydrothermal vents. On Earth, hydrothermal vents are underwater volcanoes that spews superheated water rich in minerals and chemicals. And around these vents, we find thriving ecosystems that don't depend on sunlight. Chemosynthetic bacteria use the chemicals from the vents as energy, forming the base of a food chain that includes tube worms, shrimp, crabs, and fish. Could the same thing happen in Europa's ocean? If there are hydrothermal vents on Europa's ocean floor, releasing energy and chemicals, then there's a potential energy source for life. Add liquid water and organic molecules, which we know exist in the outer solar system, and you have the ingredients for life. We're not talking about intelligent aliens. We're talking about microbial life, bacteria-like organisms that could use chemical energy from vents or radiation-created oxidants from the surface ice. But even that would be monumental. It would mean life arose independently from Earth, proving that life isn't unique to our planet. It would answer one of humanity's deepest questions. Are we alone? There are concepts for Europa lander spacecraft that would touch down on the ice, drill through, and deploy a submersible into the ocean below. The technical challenges are enormous, but not impossible. Imagine a robot submarine exploring an alien ocean beneath miles of ice, orbiting a gas giant hundreds of millions of miles from Earth. It's the stuff of science fiction, except it's being seriously planned by space agencies. Europa's interior is probably layered. At the center, a metallic iron core. Surrounding that, a rocky mantle. Then the ocean, possibly 100 miles of liquid water. And finally, the ice shell 10 to 15 miles thick. The ocean-ice interface is particularly interesting. On Earth, at the bottom of ice shelves in Antarctica, we find unique life forms adapted to living in the transition zone between ice and water. Europa's ocean-ice interface might harbor similar extremophiles. The tidal heating that keeps Europa's ocean liquid is incredibly efficient. Jupiter's gravity creates bulges in Europa's solid interior, and as the moon orbits, these bulges shift and flex, generating heat through friction. It's estimated that Europa generates about 2 trillion watts of heat, internally about the energy output of 500 nuclear power plants. All of that heat goes into keeping the ocean liquid and driving geological activity. Europa's ocean has been liquid for possibly billions of years longer than complex life has existed on Earth. If life did arise in that ocean, it's had billions of years to evolve. What could billions of years of evolution produce in an alien ocean? On Earth, life went from single-celled organisms to complex multicellular life. Fish, amphibians, reptiles, mammals, and eventually humans, all in about 3.5 billion years. Europa's ocean has potentially been stable for that entire time. Europa represents our best near-term chance of finding life beyond Earth. It's closer than Mars, more accessible than Enceladus or Titan, and has all the ingredients for life we can think of: liquid water, energy sources, organic molecules, and time. The Europa Clipper mission will tell us if the ocean has the right chemical composition for life. Future missions might confirm biosignatures. And someday, perhaps in our lifetimes, a Europa lander might drill through the ice and discover that we're not alone. But Europa isn't the only ocean world shooting water into space. 1,400 million miles from the Sun, orbiting Saturn, there's a tiny moon that's been performing the same trick. Except this moon doesn't hide its plumes, it advertises them. Let me introduce you to Enceladus, the little moon that changed everything. Enceladus is tiny, only 313 miles in diameter, small enough to fit inside the state of Texas. It should be a dead, frozen ice ball orbiting Saturn. Instead, it's one of the most active and interesting worlds in the solar system. In 2005, the Cassini spacecraft flew past Enceladus and made a discovery that shocked scientists. Massive jets of water vapor and ice particles erupting from the moon's south polar region. We're not talking about small plumes. These geysers shoot material 310 miles into space high enough to escape Enceladus' weak gravity and feed Saturn's ring with fresh ice particles. The plumes originate from four massive fractures in the South Polar region called tiger stripes, each roughly 80 miles long, 1 to 2 miles wide, and warmer than the surrounding ice. The official names are Alexandria sulcus, Cairo sulcus, Baghdad sulcus, and Damascus sulcus. But everyone calls them the tiger stripes, because that's what they look like, four parallel cracks striped across the moon's south pole. And here's the weird part. These tiger stripes are warm, relatively speaking anyway. While most of Enceladus's surface sits at minus 330 degrees Fahrenheit, the tiger stripes are minus 120 degrees Fahrenheit. That's 210 degrees warmer than the surrounding terrain. On an ice moon barely generating any internal heat, this temperature difference is massive. It means something is actively heating the South Polar region. Cassini flew through Enceladus's plumes multiple times, analyzing the material. And what it found was astounding. Water vapor, obviously. Salt, indicating contact with rock. Silicon nanoparticles, indicating hydrothermal activity. Organic molecules, including methane, ethane, and propane. Hydrogen gas, indicating potential chemical energy for life. That combination is huge. Salt and silica mean that water has been in contact with a rocky core at high temperatures, probably through hydrothermal vents. Organic molecules mean the chemistry is there for life. Hydrogen means there's a potential energy source. Beneath Enceladus's icy shell, at least in the South Polar region, there's an ocean. It's probably 6 miles thick and sits beneath about 12 to 18 miles of ice. The ocean is in direct contact with a rocky core, and that contact is generating heat through hydrothermal activity underwater volcanic vents, just like on Earth. How does a moon this small stay geologically active? Once again, tidal heating. Enceladus is locked in an orbital resonance with another Saturn moon, Dione. This resonance stretches and compresses Enceladus as it orbits, generating heat. But Enceladus is so small that it shouldn't be generating enough heat to maintain an ocean. Scientists are still debating exactly how it stays warm. There might be additional heat from radioactive decay, or the tidal heating might be more efficient than models predict. The geysers are most active when Enceladus is farthest from Saturn in its elliptical orbit. At that point, the tidal forces create the greatest stress on the moon, and the tiger stripes open wider, allowing more water to vent into space. Cassini observed the plumes brightening and dimming in sync with Enceladus' orbital position, direct proof that tidal forces control the activity. All that material shooting into space has to go somewhere. Most of it falls back onto Enceladus's surface, creating a fresh coating of fine ice particles. But some escapes and forms Saturn's E-ring, a faint gossamer ring that extends from Enceladus's orbit outward. The E-ring is made almost entirely of ice particles from Enceladus. It's the moon's exhaust trail, a constant stream of water and ice being ejected into Saturn's system. Other moons orbiting within the E-ring, like Tethys, are getting coated with Enceladus's water ice. Over millions of years, this has created bright, fresh-looking surfaces on these moons. Enceladus is literally snowmaking its neighbors. Analysis of the plume material suggests the ocean has a pH around 11 to 12, fairly alkaline. It's also quite salty, similar to Earth's oceans. The presence of hydrogen is especially tantalizing. On Earth, certain microbes use hydrogen as an energy source in hydrothermal vent environments. If similar chemistry occurs in Enceladus's ocean, it could potentially support life. Cassini detected complex organic molecules in the plumes, including some with molecular weights over 200 atomic mass units. These are building blocks for more complex chemistry, possibly even amino acids, though Cassini's instruments weren't sensitive enough to detect those specifically. Scientists have calculated that Enceladus's hydrothermal vents could produce enough chemical energy to support about 100,000 kilograms of biomass. That's not huge, but it's comparable to some isolated ecosystems on Earth. If life exists in Enceladus's ocean, It's probably sparse and localized near the vents, but it could exist. Enceladus has an advantage over Europa: accessibility. Europa makes you drill through miles of radiation-blasted ice. Enceladus? Just fly through the plumes and sample away. A future mission could analyze Enceladus's plume material with high-precision instruments and definitively search for biosignatures, amino acids, fatty acids, even DNA or RNA analogs if we're lucky. NASA has proposed an Enceladus Life Finder mission that would do exactly this, but it hasn't been funded yet. The technical challenges are lower than Europa, and the scientific payoff could be just as high. Enceladus's surface outside the South Polar region is heavily cratered, indicating it's ancient. But the South Polar region? Pristine. Almost no craters at all. This means the South Pole is being constantly resurfaced by material falling back from the plumes. The region is geologically young, probably less than 1 million years old. The tiger stripes themselves are fascinating. They're deep cracks in the ice, possibly extending all the way down to the ocean. They might be cryovolcanic vents, the equivalent of volcanic fissures on Earth, except erupting water instead of lava. When Saturn's tides pull on Enceladus, these cracks open slightly, and pressurized water from the ocean below rushes out and flashes to vapor in the vacuum of space. It's like opening a shaken soda. Instant decompression causes explosive vaporization. About 90% of the ejected material falls back to Enceladus's surface as snow. Over time, this creates layers of fine ice particles mixed with fresh water ice. Some of this material gets compacted and turns back into solid ice. Some stays fluffy and porous. The South Polar terrain is probably a complex mix of ice layers with different densities and structures. A lander mission to Enceladus could sit near one of the tiger stripes and sample fresh ocean material as it falls back to the surface. No drilling required, just collect the snow and analyze it. An orbiter could fly through the plumes repeatedly, using mass spectrometry to identify specific molecules and look for biosignatures. The science return would be enormous, and the mission cost would be lower than many deep space missions because Saturn S system is relatively close in space terms and well studied. But Enceladus isn't the only bizarre moon in the Saturn system. Just 146,000 miles away is a moon unlike anything else in the solar system. A moon with a thick atmosphere, liquid lakes, rain cycles, and organic chemistry so complex it makes Earth's early atmosphere look simple. Let me introduce you to Titan, the world where it rains gasoline and rivers flow with natural gas. Titan is Saturn's largest moon and the second largest moon in the entire solar system after Jupiter, and Ganymede. It's bigger than Mercury. It's the only moon with a substantial atmosphere, and that atmosphere is deeply, profoundly weird. Titan's atmosphere is 1.5 times thicker than Earth's. Surface pressure is 1.45. Atmosphere is 50% higher than sea level on Earth. The atmosphere is 95% nitrogen, just like Earth. But the remaining 5%? That's where things get strange. Methane, ethane, propane, and a complex soup of organic compounds created by sunlight breaking apart methane molecules and reforming them into heavier hydrocarbons. In 2005, the Huygens probe carried to Saturn by Cassini became the first spacecraft to land on a moon in the outer solar system. It descended through Titan's atmosphere, taking measurements and images the entire way down. What it found was staggering. Titan has weather. It has clouds, rain, rivers, lakes, and seas. It has seasons. It has an active hydrological cycle. Except the water in this cycle isn't water at all. It's methane and ethane liquid natural gas. Titan has hundreds of lakes, mostly near the poles. The largest, Kraken Mare, is bigger than the Caspian Sea on Earth. It's a sea of liquid methane mixed with ethane, sitting at minus 290 degrees Fahrenheit. Ligeia Mare and Ponga Mare are also substantial, each larger than Lake Superior. These aren't small puddles. They're massive bodies of liquid hydrocarbons that would dwarf most lakes on Earth. Cassini mapped these lakes using radar because Titan's thick atmosphere prevents optical viewing of the surface. The radar images show smooth lake surfaces, coastlines with bays and inlets, islands, and river channels feeding into the lakes. It looks exactly like Earth's landscape, except everything is made of different stuff. Titan has methane rainstorms. Clouds form from evaporated methane, drift with the wind, and release rain. The droplets are larger than Earth raindrops because of the lower gravity and thicker atmosphere, about twice the size. When methane rain falls, it erodes the surface, carving river channels and valleys. These channels flow toward the lakes and seas, completing the cycle. It's Earth's water cycle, but with methane. Scientists call it a methanological cycle. Titan's atmosphere is shrouded in a thick orange haze organic molecules called tholins, created by UV light, breaking apart methane and nitrogen molecules and recombining them into complex compounds. This haze blocks most visible light, giving Titan its orange appearance. But infrared light can penetrate, which is how Cassini was able to map the surface. The haze creates multiple layers in the atmosphere, giving Titan an eerie, smoggy appearance. If you stood on Titan's surface, the sky would be a murky orange-brown, and the sun would be invisible behind the haze. Titan's surface is a mixture of water ice, which at minus 290 degrees Fahrenheit is as hard as rock, and liquid or frozen hydrocarbons. There are dunes made of organic particles, mountains made of ice, cryovolcanoes that might erupt ammonia-water mixtures, and vast plains covered in liquid methane and ethane. The Huygens landing site showed rounded cobbles made of water ice, smoothed by flowing liquid. The ground was described as having the consistency of wet sand or cream broly, a thin crust over something softer. Near Titan's equator, there are massive dune fields, linear dunes, that can stretch for hundreds of miles and reach heights of 300 feet. But these aren't sand dunes. They're made of organic particles, basically hydrocarbon soot that settles out of the atmosphere. It's dark, fine-grained material that behaves like sand in Titan's winds. The dunes are shaped by Titan's prevailing winds and look remarkably similar to dune fields on Earth, in places like the Sahara Desert or Namibia. Same physics, completely different chemistry. There's evidence of cryovolcanism on Titan volcanoes that erupt liquid water mixed with ammonia instead of molten rock. These cryovolcanoes might occasionally release pockets of liquid water from Titan's subsurface onto the surface. And here is where it gets interesting for astrobiology. If pockets of liquid water exist beneath Titan's surface, heated by tidal forces or radioactive decay, those could potentially harbor life. Titan's surface is far too cold for liquid water, but subsurface pockets could exist at temperatures where water is liquid. And Titan has all the organic molecules you could want. It's swimming in organic chemistry. Cassini has measurements of Titan's gravity field, and rotations suggest there is likely a subsurface ocean beneath the ice crust, probably a mixture of water and ammonia, sitting 35 to 50 miles below the surface. This ocean is separate from the surface methane lakes. The surface lakes are liquid methane at minus 290 degrees Fahrenheit. The subsurface ocean is liquid water mixed with ammonia as antifreeze at potentially habitable temperatures. Titan is essentially a giant laboratory for prebiotic chemistry, the kind of chemistry that might have preceded life on Earth. The organic molecules being created in Titan's atmosphere are similar to those that existed on early Earth before life arose. Studying Titan helps us understand how organic chemistry progresses toward biochemistry. Some scientists speculate that if Titan had liquid water on its surface instead of liquid methane, life might have already arisen there. The organic chemistry is that rich and complex. There is even speculation about whether life could exist in Titan's methane lake's life based on liquid methane as a solvent instead of water. On Earth, all life uses water as its fundamental solvent. But there's no fundamental law of chemistry or physics that says life must use water. If you have a liquid solvent, organic molecules, and an energy source, you potentially have the conditions for life. Methane-based life would be radically different from Earth life. Different biochemistry, different metabolism, operating at minus 290 degrees Fahrenheit. But different doesn't mean impossible. Titan receives very little sunlight. It's nearly 1 billion miles from the sun. But there are potential energy sources. Chemical reactions between hydrogen and acetylene, created by sunlight, breaking apart methane. Tidal heating from Saturn radioactive decay in the rocky core. Impacts delivering heat. Whether these energy sources are sufficient for life is an open question. But Titan has the raw materials and the liquid environments. The question is whether it has enough energy. Cassini studied Titan for 13 years, making 127 flybys of the moon. It mapped the lakes, tracked seasonal changes, measured atmospheric chemistry, and revealed Titan to be far more complex than anyone imagined. Seasons on Titan last about 7 Earth years, because Saturn's year is 29 Earth years. Cassini watched as the northern lakes filled with liquid during northern spring, while southern lakes evaporated. It's a global redistribution of methane, happening over decades. In 2027, NASA will launch Dragonfly, a nuclear-powered quadcopter designed to fly through Titan's thick atmosphere, exploring multiple sites across the moon's surface. Dragonfly will land at various locations, analyze surface composition, search for prebiotic chemistry, and study Titan's methane cycle. It's scheduled to arrive at Titan in 2034. This will be the first mission to fly a powered aircraft on another world besides Mars's Ingenuity helicopter. Titan's thick atmosphere makes flight easier than on Mars, but the cold and distance create other challenges. Titan is often described as a frozen early Earth. Its atmosphere is nitrogen-rich, like Earth's was before oxygen appeared. Its organic chemistry is similar to Earth's prebiotic chemistry. Its weather cycle, erosion, and sedimentation are Earth-like. If you warmed Titan up and added liquid water to the surface, you'd have something resembling early Earth, a world rich in organic molecules, ready for life to emerge. But Titan, Europa, and Enceladus are all moons. They're fascinating, but they're small. They orbit bigger, far stranger worlds. Now it's time to talk about the gas giants themselves, planets so massive, so alien, so fundamentally different from Earth that calling them planets almost seems wrong. These aren't worlds you can land on. They're worlds that would crush you, freeze you, tear you apart with winds, and subject you to pressures that turn hydrogen into metal. Let's descend into Jupiter, the king of planets, and see how long we'd survive.